topic. Okay, so the last session we have discussed about the confidence interval and confidence level. And also we discussed about the different types of sampling techniques. And today we will take a look at the hypothesis testing. It's one of the important topics in data science or statistics. Okay, so what is hypothesis testing? It's the process of determining whether or not a given hypothesis is true. Okay, so the hypothesis testing is also called as a significance testing. So this the another name for this one is significant testing. So basically, the statistical hypothesis is about an assumption about a population parameter. We make an assumption about a population parameter. So what do you mean by parameter? So I discussed about the population mean mu. So we use the notation mu for the population mean. This is my population mean, and sigma is the population standard deviation. Okay, and the sigma squared is population variance. And when it comes to sample, instead of mu, we use x bar to represent the sample mean. And instead of sigma, we use small s to represent standard deviation. So these are called statistic, and these are called parameter. Anything regarding the population, we call it as a parameter, and sample we call it statistic. We use statistic to estimate the population parameter in simple terms. So that is what we do it here. So basically we are we are hypothesizing an assumption about a population parameter. Okay, so in the case of hypothesis testing, in general, we use sample data to evaluate a question about a population. Okay, it examines two hypotheses about a population. You have something called null hypothesis and alternative hypothesis. The alternative hypothesis is a contradicting statement about your null hypothesis. Okay. So what is a null hypothesis? Hypothesis to be tested, and alternative is the hypothesis that we use as an alternative to the null hypothesis. It is the opposing statement of my null hypothesis. That is what is called as alternative hypothesis. There are different types of hypotheses are there. One is the one sample Z test and D test. So in this case, we are going to use a single sample, and we have two independent sample T test. So we use two sample, but those two samples are independent from one another. And the next one is the paired sample T test. Okay, in this case, we use the same sample, but it is the sample is same. It is not independent. Okay, and next one is multiple sample test, that is called your analysis of variance, and finally the non-parametric test called chi-square test. We will see how much I can cover in today's session. Just a quick comparison about the different types of hypothesis test. So at a high level, right? So for the discrete variable and continuous variable, right? So we can do the hypothesis testing. In the case of continuous variable, we compare two groups or single group. Okay, and so here basically we are going to compare the sample mean with the population mean. So the same thing here, in this case, comparison of more than two groups. If I have more than two groups, if I have a single group or two group, then I can go for either Z test or T test. Again, there is a caveat here. So if you know the population standard deviation, then you can go for Z test. If you don't know the population standard deviation, then go for T test. If you have more than two groups, what test can I use at ANOVA? It is pretty simple. So now you understood. If I don't know my population standard deviation, then T test. If I know my population standard, Z test. And this is applicable only for single group, single sample, or two independent samples. But if I have more than 2 samples or 2 groups, then you need to use ANOVA test. Next one is the discrete type of variable. In the case of discrete type of variables, if you are using more than 2 groups, then use chi-square test and comparison of 2 or 2 a number, 1 or 2 proportion test, we do it. Okay. So what we will do is, first of all, let us understand the intuition behind the hypothesis testing. So let's take this simple example. For example, you bought a Lay's chips packet. On top of the chips packet, they printed it as 235 gram. When you unpack this packet, you will find 235 gram quantity of the chips inside of this packet. Okay. So now you wanted to test it out. Okay, you're not believing this. You want to test it whether it really has 235 gram or not. So what you're doing is you are buying the voice is not clear. How about others? Mukilan found my voice was not clear. How about, is that the same with others? Probably Mukilan, you can log in with other mobile phone or laptop so that you should be able to hear. Others do not find any issues. Fine. What do you mean by yes, sir? So my voice is not clear, Mala? Clear or not? Say yes or no. I'm hearing your voice twice. Oh, okay. 1 second. Let me just check it out. So it is echoing, right? So where the problem is, let me just check. Is it okay now? Is it okay now? Double echoing, right? So don't say double echoing. So is it okay now? Let me just check everybody. Yeah, I need to mute everyone. I think now the issue will be over. Is it okay now? I think it should be okay, right? Say now it is okay. Now it's okay. Don't say yes, sir. Okay, and now it's fine. Okay, good. Okay, okay. So now what I do is I want to conduct a test to validate whether this packet, each packet has 235 gram quantity of the chips in it or not. So what I do is I just go and collect some samples. I go and buy the chips packet from different shops. And then I unpack all these packets and then I'm going to weigh it. So, and after weighing all these packets, each packet's weight, and then when I take the average, I get, let's say if I get 200 gram. So what can we do? So can I say the claim made by the manufacturer is correct or not? See, the on top of the packet, they printed it 235 gram, which means each packet has 235 gram quantity of chips in it. What I did, to test this, I bought 15 packets from different shops and then I unpacked it. And then after I weighing it, I could see that the average quantity of the chips packets, all these 15 packets put together, right? When I take the average, I'm getting 200 gram. But the whatever they mentioned on top of the packet was 235. But whereas when I bought a sample, when I took a sample, and with that sample, I could see 200 gram. So can I accept the claim or statement made by the manufacturer, or can I say I'm going to reject the statement made by the manufacturer? What will you do in this case? Obviously, it is pretty straightforward. By my sample, as per my sample, my sample size is 15 here, and I'm getting 200 gram on an average, the quantity of chips in these packets. So obviously I'll have to reject it because it is way too high, right? So way too low. So 235 gram, but it is only 200 gram is there on an average. Supposing when I unpack all the 15 packets, and if I find 230 gram, is it okay with you all? What do you conclude here? What do you conclude? Are you okay with this? The year 230 gram, I'm getting it after unpacking these 15 packets. And if I weigh it, the average amount of chips in these 15 packets, right, in each packet is, so let's say, 230 gram is there. But they printed 235 gram, but whereas 230 gram is there. Are two scenarios. One is 200 gram and 230 gram. If it is a 200 gram, it is way too high. Right. So since it is 230 gram, since the difference is very small, it is negligible. That is what Mukilen's point of view. Very good. How about others? How about others? Others are also think the same way, or we have different points of view? What is your thought here? See, it's simple here. You go and buy 15 packets and you unpack it and weigh it, and you take the average. In scenario one, you are getting 200 gram, but obviously you go and say, yes, whatever the statement made by the manufacturer was not correct. I'm going to reject it because it comes around 200 gram only. But here in this case, it is somewhat close to this, right? Hence, we cannot say that I'm going to reject the statement made by the manufacturer. Here, the assumption was the statement made by the company or the manufacturer, right? So we are hypothesizing it based on the value that he printed on top of the packets. We mentioned 235. We are assuming that each packet will have on an average 235 gram it will have in it, but in scenario 2 I'm getting 230 gram. So still I'm not going to reject it. Again, depends on depends on the policies set by your company. So 235 gram. Now let us visually look at this. 235 gram is the average, right? Average will be there in the middle. Let's assume that this is a normal distribution. In the 235 gram is there in the middle because this is an average, right? So on an average, each packet will have 235 gram in it. Fine. Supposing I get 220 gram after I do the test with my sample, the average is 220 gram. So is that okay? Is that okay? 230 gram is somewhat close by. 220 gram, it depends on the company policies. For example, your company is very reputed one. You don't want to spoil the reputation. You don't want to spoil the reputation. And as a quality inspector, you want to pass this test, okay, because you don't want to spoil the reputation of the company. If it is 220 gram, you are a little bit liberal now. Even if there is a 15 gram difference, let it be there. Even if there is a difference, let it be there, right? Let it be there. So, but it should be anywhere between 220 gram to 235 gram. So, okay, if it is anywhere between 220 gram to 235 gram, it is okay. 220 gram is obviously less than 235 gram. Okay. And let's say you have another scenario. If anything less than 220 gram, you are going to reject it. So this is called your RR region, rejection region. Anything, this is your cutoff value. My cutoff is 220 gram, tolerance level. If anything less than 220 gram, and if that falls here, that I'm going to reject it. Since the 220 gram or less than 220 gram, it's all falling in the left side, we call it a left tail test. Or one tail test, okay, left tail test. So this is called your rejection. Anything less than 220 gram, I'm going to reject it. So I'm not going to accept the statement made by the manufacturer, but still I'm okay with 220 gram. Okay, 15 up to 15 gram I can tolerate. Okay, so now if I write the statement, right, hypothesis, null hypothesis, and alternative hypothesis. The null hypothesis, we use this notation H sub 0. So the average amount of chips in the pack is 230. We are simply assuming that whatever somebody says is true. That is what your null hypothesis. And the alternative hypothesis use a notation H sub A, or in some case they use 1. Okay, 1 means alternative hypothesis. Average amount of chips in the packet is less than 235 grams. So what we are interested is less than. Okay, anything less than, if you find it, that is left tail test. Okay, anything less than the statement made by your manufacturer, we call as a left tail test. Anything less than the cutoff value, so this is called, this, it will fall here, right? So 219 gram will also fall here. So hence this is called your rejection region area. Since the rejection region is area in the left side for the left tail test, importantly, we are very particular about less than. See, as a customer, we are very particular about less than. It should not be less than what they promised. If it is anything more than that, we don't care, right? If you find 250 gram is there, after you unpacking your sample packets, will you comply? No, you will not make any complaint. You simply keep quiet. Anything less, you are going to raise a concern, right? So the average amount of chips. So you want to test this one. I want to check if this is less than 235 or not. Again, we are going to define a cutoff here. So since it is less than left tail test, and let's say if it is more than that, so that is called your right tail test. 235 gram is the average, and let's say you have something called 250 gram. Up to 15 gram per packet, I can have the excessive quantity of chips packaged in it. Okay, I'm fine with that. But anything above 250 gram, it falls in the rejection region area. So sorry, this is the rejection region area. Okay, this line, it's like India-Pakistan border. Okay, so rejection region area. This is called your RR, rejection region area. If it is 251 gram to anything above 250 gram, I'm going to call this a rejection region area. I'm okay with 250 gram also, up to 230 grams. So that means overfilling. Each packet, it is overfilling. And what I do is I do some kind of pros and cons, and so the machines are filling each packet with 235 grams. Sometimes some machines can fill 250 gram also, 235, 240 gram, 242 gram. It will not be exactly 230 gram. Some variance will be there. Even if the variance is slightly excess or more, I'm fine with that. So how much I'm okay to 250 gram, because there are the machines are not so brand new, and it's all 10-year-old machines. There will be, since due to wear and tear, the machines, we cannot expect the accuracy, right? So there will be some kind of variation. And if I'm so sensitive about the variation, then obviously I have to replace the older machine with the newer one. Buying a new machine is an expensive one. In that case, I'm going to do some kind of trade-off. Up to 15 gram per packet, if it fills, let it be there. Instead of spending money in buying a new machine, let it be. If anything to 50 gram, it is cost for the concern. Per month, if I spend, let's say if I sell 100,000 packets, and per packet, if I lose 20 gram, I'm gone, right? So 20. So you are going to lose 2 million, right? So 2 million gram per month. Right? This is way too high. Okay, so what you're doing is you need to decide. In that case, you need to see if it is anything more than 250 gram, then you'll have to buy a new machine. Okay, so if it is a lesser quantity, it is a problem for the customer. As a manufacturer or a QA person, right? You don't want the both condition, right? So if it is, or as a manufacturer you're concerned, if it is more than this one, then it is going to shoot up my margin. So what I do is, so in this case, this is called a right tail test. Anything more than 235 grams. So in the null hypothesis, you say 235 grams. In the alternative, average amount in the packs is not 235. It is more than 235. That is what you are going to do the test here. And this is called your right tail test. because greater than sign, you can see you are using it here. Next one is two-tail test. It should not be less than 230 gram. It should not be greater than 240 grams. In both the side, the left and right side, you are going to define the cutoff here. So the cutoff is this one. Okay, this is just a straight line. Okay, the white color is the line. This is the border. So anything less is also problem. Anything more than this one. So you are going to define two cutoff here, two tail test. So in the case of manufacturer, they are supposed to do two tail test because they don't want the machines to underfill it. They don't want the machine to overfill it. Both of them cause problem. Overfilling can hit my margin, and whereas my underfilling can damage my reputation. This guy is not a good guy. Okay, so you mentioned something and it shows something else. So in that kind of situation, you need to use two tail test. So in this case, your null hypothesis will be like something like not less than, not greater than, not equal to. Average amount of chips in the packets is 235 grams. If you find not equal to, that means two tail test. It could be either less than the average quantity or greater than the average quantity. That is what not equal to. If it is less than, that is a left tail test. And let's say as a customer, you are very particular about less. And you don't care about excess thing, right? As a manufacturer, you need to see this one also greater than, right? So sometimes the quality inspector, they want to make sure that it should not fill more than what we promised from the revenue point of view. And these are the steps that we need to follow in order to perform hypothesis testing. The first step is you need to define the null and alternate hypothesis. Next one is you need to collect the sample data, and then you need to calculate the test statistic. This is some formula, okay? And if the formula, the test statistic value is less than something or greater than something, if that falls in the rejection region area, then we are going to reject it or fail to reject the null hypothesis. Either you reject or you do not reject. And finally, you draw a conclusion. These are the 5 steps that we follow when we do any hypothesis testing. So, okay, so we use H sub 0 notation to define the null hypothesis. The null hypothesis is nothing but what you assume to be true. It is usually always uses an equal sign. An hypothesis of equality. Null hypothesis. Remember this. Alternative hypothesis, what you attempt to demonstrate, what you want to test. It is usually an inequality. It should be less than or greater than or not equal to. The alternative is usually an inequality. The null hypothesis is usually an equal sign. We simply assume whatever somebody says. Okay, that is what your null hypothesis. Next, we will take a look at this one. How do we define the null hypothesis and alternate hypothesis? For this case, a manufacturer states that the average life of a car battery is 24 months. Write the null and alternate hypothesis. Why don't you type it in the chat window? What is the null hypothesis here? Somebody says the average life of a car battery is 24 months. Write the null and alternative hypothesis. Let's say you are from the customer point of view. If it is less than 24, you are concerned, right? Or from the manufacturer point of view, Sumiti, yes, null is 24. Very good, right? So the H sub 0, null hypothesis, mu is equivalent to, we assume that the population means 24 months, because this is what the statement made by the manufacturer. And what is the alternative hypothesis? So can we say the mu is not equal to 24? It is not less than 24. It is not greater than 24. We can say that way also, right? No, it is less than 24 months. Whatever they mentioned was not correct. It is in my car, it lasted less than 24 months only. In some cases, it is greater than more than 24 months. right? We can say this. The average car battery is 24 months. Okay, alternative hypothesis, the average car battery is not 24 months. Not equal to, right? So you need to use this sign not equal to here. So this is my null hypothesis. This is my alternative. It could be less than 24 or greater than 24. There are two possibilities here. Next, you tell me what is the null and alternative hypothesis. It's a very interesting one. At least, we can see the at least. At least 100 gram, write the null and alternative hypothesis. What is the null hypothesis? What is the alternative hypothesis? Let me see how many of you give the correct answer. No, not 100 gram. Here, that's why I highlighted red in red color. Okay, at least. In statistics, if you find at least contain less, at least is greater than or equal to, right? At least, at least 100 or more than 100. That is what at least statement says. Yes, null is more than or equal to 100. Yes, you are correct, Sumiti, right? So here, so that's what mu is the null hypothesis. We are assuming that 100 or more than 100. That is what at least says. What is at most? What is the difference between at least and at most in statistics? At least is if somebody says at least 200, which means 200 or more. If it is at most 100 means less than or equal to. Remember these two terms in statistics, okay? And see what is the null hypothesis here? Same thing. So mu is greater than or equal to 100 and mu is less than 100. We won't test. No, it is not 100 gram or more than 100. It is less than 100. Okay, so now you understood what is at least, right? If you find this clause at least, then it is greater than or equal to. At most is less than or equal to. Let me see how many of you can give a correct answer. Here we did not see any at least or at most, and we don't see equal sign or also. Here we can see more than 6 hours per day. What the manufacturer says, more than 6, right? 100 gram contains more than 100 gram. Okay, more than 100 gram. Lesser than or equal to. Okay, so Mugilan has made an attempt. Okay. Is more than 6 hours per day. The manufacturer claims that the number of backup hours per day is more than 6 hours per day. So we say like that this one is greater than 6 and mu is less than or equal. So you want to say no, it is 6 hours or it is less than 6 hours. Okay, since they have mentioned already more than, so we can also rewrite something like this. Okay, and mu is less than or equal to say, and S sub A is equal to mu is greater than 6. We can say this way also. This is what my null hypothesis. This is what my alternative hypothesis. So to overcome this thing, right, what they mentioned, what in practice we do is less than or equal to or greater than or equal to, we replace them by equal sign in the null hypothesis. Okay, simply you put equals to 6. That means, which means it could be either less than or greater than. It is not equal to, right? So something like that. We are going to test it out in the alternate hypothesis. Hope with this example you are able to understand and what exactly left tail test, what is right tail test, anything less you want to do. If you want to test or if you think suspicious or you want to test something less than whatever the quantity mentioned by someone else, that is left tail. And if you think whatever mentioned by someone is not same as what we expect, because it could be more than that, that is what the right tail. Two tailed is both. And two tail test In the alternative hypothesis, you need to use not equal to, which means both sides you need to test it out. And left tail test less than, right tail test is greater than. And you need to remember this table, but you don't have to memorize this one. So we have something called alpha values. The alpha is the level of significance. Okay, and as 0.05 is the one in general is used. And how many of you remember the confidence level which I discussed yesterday? Not the confidence interval, the confidence level. If somebody says, ask you a question like, what is the how confident are you that you can come to office tomorrow between 9:30 to 10:30? Okay, the confidence level 9:30 to 10:30, that is a range. The confidence level is something like how confident are you that you are going to at least make it between this time. Confidence level, we discussed it, right? So yesterday. And I told you yesterday, so 95% confidence level, and we can say 99% confidence level and 90% confidence. If you say 99%, you are taking the sample, but you cannot say 99%. Even if you wanted to say something 99% confidence, then the interval range will be very wide. And if it is very wide, and if it is very less, and it should be optimal, right? So 95%, always it is good if you say 95% confidence, because you are taking the sample data, you're not taking the population data. Okay, we discussed about different types of hypothesis. One is the Z-test. Look here, this is what we discussed, right? Z-test and T-test. If you are using a single group or two group, you can use Z-test or T-test. Now we will start with understanding what exactly Z-test is all about. So far we understood the basics of the hypothesis test, like what is the left tail test, right tail test, two tail test. Now we will continue and take a look at the one sample Z-test. If you know the population standard deviation, then you can do Z-test. So what are the steps that are involved to conduct the Z-test? Whether Z-test or T-test, first step is you need to define the null and alternative hypothesis, and you need to specify the significance of the alpha. And the next one is you need to determine the critical region. Critical region, nowadays we don't use it. Instead, we use p-value. Anyhow, if you know a critical region is also good, because there are some interviews they'll ask you this one also. And the next one is calculate test statistic. The fourth step is calculate the test statistic and find the p-value. And is the sample result in the critical region? If it is falling in the critical region, then you are going to reject the null hypothesis. Or if it is not falling in the critical region, you are failed to reject the null hypothesis, and you are going to draw a conclusion. Forget about all these steps. At the very beginning, when you learn hypothesis, difficult to remember all these steps. When I start with the problem statement and when I walk you through the solution for this, you'll be able to understand all these steps practically. Let's say a car manufacturer claims a specific model of the car, their brand's car, right? So it gives 25 miles per gallon, and the standard deviation also they've given. So this is my population, mean population standard deviation I know. Since I know my population standard deviation, I can conduct Z-test. Okay, a consumer group asks 40 owners of this model to calculate their miles per gallon, and the mean value was 22 with a standard deviation of 1.5. Is the manufacturer claim supported? First of all, what is the null hypothesis here? Mu is equal to 25. The manufacturer says the model, this specific car model of my brand gives 25 miles per gallon. What is the alternative hypothesis? As a customer, we are suspecting that it cannot be 25, it should be less than 25. And next one is establish approved strategy and sampling distribution. This is a left tail test because less than sign. And statistical test is Z-test because we know the population standard deviation, it was given. Next step is the type 1 error rate, significance level. In here, you need to specify the alpha value. So the it's something like, type 1 error rate, specify the type 1 error rate or significance level. Both of them are same. So here we are determining the probability threshold for making decision to reject whether the null hypothesis is true or not. Okay, this probability is called the level of significance. It is denoted by alpha. We use something called alpha notation to define the significance level. And the alpha values in general, what we do is we use 0.05. Or in some cases, we use 0.01. And some other cases, we use 0.10. So what is the total area under the curve? I told you it is 1, right? And 1 minus alpha. You need to do it. Why should I subtract alpha from this one? Because here we are conducting less than, right? It could be less than whatever they define. For example, the 25 miles per gallon is there in the middle, the average. It can be less than that also. There could be chances. I'm going to define a cutoff value. So if it is up to 23 miles per gallon, I'm okay. Anything less than 20, I'm going to reject it. Right? So up to this, so this line is my border line, right? This is my border line, the black colored one. Okay, that is my border, and that means anything falls less than the critical value or the cutoff value that falls in the rejection region. I'm going to reject it, reject the statement made by the manufacturer. So right, so the total area is 1, but there is a chance that it can fall in the rejection region area, right? So this rejection region, I'm going to say alpha is equal to 0.05. So left tile test. And next one is I'm going to say the decision rule. I'm going to specify the decision rule. If the z value is less than 1, z value is 1.645, greater than that, rejected, else reject, else. If it is less than this one, also rejected. Greater than this, rejected. Less than this, also rejected. And what is my sample data? N is equal to 40. See, my consumer group was 40 owners. Sample. We are running a survey with 40 car owners to find out whether really they are able to get 25 miles per gallon. Okay. You cannot call all the customers who bought a specific model of a car. Instead, randomly you are sampling it. Your sample contains only 40 owners. And since you called people and you asked each and every person how much mileage you are getting it. Some people say 24 miles per, some say 22, 20 and all. You can take 40, since you have 40 owners data, you can find out the average, right? When you found the average of your sample, you got 22 miles per gallon. And the standard deviation is 1.5. Now we need to test is the manufacturer claim supported or not. Okay, here I have used something called Z test. So there is a formula for Z. Okay, if the Z is greater than Z. So what is the formula for Z? This is the formula. Sample mean minus the hypothesized mean. What is my sample mean here? 22, right? You need to simply plug in this value 22 minus. What is the hypothesized mean? We are simply hypothesizing whatever they are saying is correct, 25. Actually, we use the notation 0, hypothesized mean. So 22 minus 25 and divided by sigma. We know population standard deviation. What is population standard deviation? Here the population standard deviation is 7. Simply you plug in here in the denominator is 7 and square root of n. So what is n is for 40. 40 customers we ran a survey. When you subtract this value in the numerator and if you divide this one, you get this value. This is what your z value. This is nothing but your z value. My z value is minus 2.171. What is the decision rule? If the z value is less than 1.645, I'm going to, greater than 6, I'm going to reject. And two-tail test. Okay, you can do two-tail. If it is less than minus 1.6, now you tell me whether minus 2 is less than minus 1 or not. Let me see how many of you know this. And some people, most of them in the previous batch, even they could not So whether -1 is less than -2, can someone tell me? Is that true or not? Come on, yaar, it's high school math. So 1 is obviously less than 2. Can I say -1 is less than -2? Is that true or false? What happened? No one responded. You forgot the elementary school math. -1 is false. -1 is less than, sorry, okay. Say, let's say -2 is less than -1. Is that false? -2 is less than -1. Is that false? -2 is greater than -1. Come on, yaar. True, right? Yes, Mukilan is true. -2 is less than -1 is true. Okay, so what is the z value? Put the z value. -2 is less than -1. Obviously, right? If something negative means depth. So if you have more, the value, more depth you have. Right? So yeah, so that is the thing, right? So you're going to reject the null hypothesis. Now the question is, how did I arrive 1.645? Okay, so now we have a table for that. In the, if you look at the school math book, at the end of it, you will find something like this. 1.645. I don't know whether I put it here or not. So you need to find out the critical value. I was talking about the cutoff value, isn't it? Cutoff value is nothing but the critical value. Just think that way. Because for you people to understand the cutoff value here, right? I mentioned some example. Okay. For you people to understand, if I told you critical value, wouldn't have understood. Okay. And instead I told you cutoff value. If the cutoff value is less than 25 miles per gallon, fine, but if it is less than this cutoff value, then it is following the rejection. That's what I was telling you, right? In fact, there is nothing like cutoff value. Instead of cutoff value, we say critical value. So 1.645, we need to see, okay, here 1 minus alpha. What is my 1? 1 minus alpha is 0.95. Okay, let me just go to the Z table. We have something called Z distribution table. 1.6, look here. 1.6, and see, what is this one? The total area under the curve is 1, right? And alpha value I'm going to consider 0.05. 1 minus 0.05 is 0.95. So we need to find out where the 0.95 is located in this Z distribution table. And somewhere we can see here 0.9505 is there. It is slightly bigger than 0.95. Here, on the other hand, 0.9495, it is slightly lesser than 0.95. So which means in between these two values, somewhere here, the 0.95 will be there. So if you add 1.6 plus 0.4, 1.645, you will get that one. So horizontally and vertically, you need to see it here. Got it? So 1.6, the horizontally and vertically where it intersects. Right, so we are assuming that the 0.95 is between, obviously it should be somewhere between these two values. The star, that is what the star marks it here. So here, what is the corresponding horizontal value? 1.6 in, and what is the corresponding vertical? 0.4 and something between, right? So here 1.645, something like that. So 1.6 plus 0.04 is 1.645 something we are getting. That is how we arrived the critical value. 1.645. Okay, we cannot say 1.650 because 650 is 0.9545, something like that. So 1.645. So if it is a right tail test, it is a positive value. If it is a left tail test, it is a negative value. Since the test that is inside the resistance region we reject the null hypothesis. Since -2, now you need to the z value is -2 and odd. So -2 is obviously less than this one, it is true. Hence it is falling inside the rejection region area. Hence we reject the null hypothesis. And we conclude that there is no sufficient evidence to support the manufacturer's claim. We don't have sufficient evidence to conclude the statement made by the customer. So hence we are going to reject the null hypothesis. So the steps are pretty simple, right? So the 1 minus alpha is, we are going to consider the significance level also, right? So the total area under the curve is 1. And there could be chances that it should be less than 2 points. So the critical value, right? So critical value, you have to find it out. The critical value, now you understood, 1 minus alpha gives you 0.95. 0.95, when we looked up in that Z distribution table, horizontally and vertically, we could see the 1.645, it is coming it. And as per the formula, we are getting the Z value is -2. Since -2 is less than the critical value, -1.645, it is falling in the rejection region area. Hence, we are going to reject the null hypothesis. And we going to conclude that we don't have sufficient evidence to support the statement made by the manufacturer. Okay, now the question is, so the alpha value is 0.05, and can't I use 0.01 or 0.10? Okay, what is the total area under the curve remains still 1 only. But if I choose 0.05, it will be somewhere here. And if I use, for example, this is the one is related to my alpha equal to 0.05. So if I use 0.05, what will happen is the non-rejection area size from here to here, this is non-rejection region area. Non-rejection area size increases. The width of non-rejection area increases. But when I use alpha equal to 0.01, the cutoff value, right? It starts from here itself. Hence, it becomes too wide. The non-rejection region area becomes too wide in the case of alpha equal to 0.01. If I use alpha equal to 0.010, the rejection, these are all rejection region area. If I use 3 different values, what is going to happen? When I use alpha equal to 0.010, the cutoff region starts here itself, which means this one becomes, narrow, right? The width is very less. It is reducing the non-rejection region area. You understood? So when you keep reducing the alpha value, the non-rejection region area size is getting bigger, bigger, bigger. In that case, what will happen is sometime even the true null hypothesis can also, false null hypothesis can also fall in the non-rejection region area. Okay, so there could be chances. So that's the reason why what we do is we don't want to increase the non-rejection region area size like anything. And also we don't want to reduce the non-rejection region area. So you want to use some optimal value like all alpha equal to 0.05. Usually we use alpha equal to 0.05 only. But in case your testing process is very stringent, in that case you'll have to use either 0.01 or 0.1, sorry, 0.1. If it is stringent, 0.1. Take the same chips example. You are conducting some kind of quality test, internal quality test, and even if the chips packet consists of less than, let's say 235 gram should be there. Even if it is less than 225 gram, I'm going to reject it. Your rejection region area size is getting increased when you specify the alpha value is 0.10. You understood? So this is what your 225 gram. Or if you say, no, even if it is going to be 230 gram, it is fine. So in that case, your rejection region area size is going to be less. When you use alpha, you are so liberal. You are saying even if it is going to be 200 gram, I'm okay with that. Somehow you want to pass the test. You want to accept, you don't want to reject the null hypothesis. Right? So if you specify 0.01, what will happen? The non-rejection area becomes very big, right? See, it's something like goal post here in school. If the goal post is very small, what will happen? What will happen? The chance of hitting the goal is very remote, right? Because the goal is 6.2 feet height, and you can jump here and you can block it. If it is too wide, what will happen? The chance of hitting the goal is very high. That's what. If alpha equal to 0.01, still it can fall in the non-rejection region area. If your null hypothesis actually false, in that case, it should get rejected, right? So in that case, what will happen is, even in that case, the false null hypothesis will fall in the non-rejection region area. You ended up not, your false null hypothesis supposed to be get rejected. Since your alpha value is 0.01, the goal post size is very big. Hence, you are going to, you're not supposed to reject your null hypothesis. Okay. Since it is falling in the rejection region area because of the value is very less, you are rejecting the null hypothesis, whereas you are not supposed to reject the null hypothesis. Okay, if it is a false null hypothesis, you are going to, if it is a true null hypothesis, you are not supposed to reject it, right? So you can watch my video one more time, so that because certain things, you cannot understand in one go. That's why I use that analogy goal post. If the goal post is very bigger, what will happen? The chance of hitting the goal is very high. So in this case, the chance of rejecting the null hypothesis is very high. If the goal post size is very big, that means if the alpha value is very less, the chance of rejecting the null hypothesis is very high. Okay, so the critical value, I was talking about critical values, it's not used in practice. Even if you use any package in Python or R language or any other language to conduct the statistical test, the z-test, p-value method is the one widely used. Remember that if the p-value is less than alpha, reject the null hypothesis. This is the universal truth. Even if you do statistics in PhD, this rule is applied. Okay, so that's why in statistics, conducting any test and interpreting them is very, very easier. If the p-value is less than alpha, reject the null hypothesis. When you run a test package, okay, so the function name, hypothesis test function name is like 1t something like that, and you need to specify the argument. It will return the p-value. If the p-value is less than alpha you need to keep at the top of your head, 0.05 only you'll be using it. The p-value is 0.001, right? That means obviously p-value is less than alpha, reject the null hypothesis. Okay, so most of the statistical test, it will return p-value only. So if it returns p-value, your job is pretty simple. You know what is alpha, 0.005, that is there on top of your head. And the p-value has to be given by your the function or the method or the package. If the p-value is 0.01, yes, it is less than 0.01, so I'm going to reject the null hypothesis. If the p-value is greater than alpha, you cannot reject the null hypothesis. Here, look here, this is my z value, minus 2.71. So the p-value method, how I can obtain it, since it is a left tail test. Look here in the middle one, if you divide this one, the normal distribution, right? On the left side, it is 0.5. On the right side, it is 0.5. The total area under the curve is 1. But if you bisect this one, okay, if you cut it in the middle, the left side is 0.5, right side is 0.5. Since we are conducting left tail test, 0.5 minus this value 0.496 is how I arrived at minus 2.71. You need to do a lookup in your table here. Look here, the z table, 2.701 minus 2.71, right? The z value. For the z value, you need to do a lookup in this table. So here it gives 0.9966 and 0.9966. Okay, so here there's a left tail test, right? So you need to take into account also 0.27, 0.01, 0.0034. One second, let me just minus what is the value? To the z value is minus 2 points. Sorry. The z value is minus 1.46. Minus 1.46 is going to be look here, minus, so in this case minus 1.4 and 6 is there here, right? So it intersects minus 1.4, it intersects minus 0.0721. So here, look here, 0.5 minus, so here it gives us directly the p-value. Okay, so you don't have to subtract this one, 0.279 and all. It gives you 0.0721. This is your p-value. So z table lookup of minus 1. So you need to do a lookup of this value, minus 1.46, where it is there. So it gives you directly the p-value. Is this p-value is less than alpha? Forget about this step. Okay, so we are, since if you do a lookup of this value into your z table, okay, you get 0.0721. This is what your p-value. What is alpha? 0.05. So can I say the p-value is less than alpha? No. In this case, the p-value is greater than alpha. Hence, we fail to reject the null hypothesis. And we are going to conclude that whatever the statement made by the manufacturer was correct. Okay. So p-values, in the case of p-value, we need to look up the z value into our z distribution table to get the p-value. That is pretty simple. Next, we will take a look at the one sample t-test. Okay, so if you don't know the population standard deviation, then you need to do the one sample, it's a t-test. You need to do the t-test. If you are going to use a single sample, then you need to use the one sample t-test. But there is some rule here. If the sample size is less than 30, so right. So if you don't know the population standard deviation, and also if the sample size is less than 30, then only you can do the t-test. In other words, you must know the standard of the population and your sample size must be above 30 in order for it to be, you would use z-score, otherwise use the t-score. So this is the formula for conducting the t-test. So what is the difference between z and t-test formula? They're also the same thing. Here you have sigma divided by square root. You know the population standard deviation. Here in the case of t-test, student's t-test, is also called as a student t-test. In the case of student t-test, we do not know the population standard deviation. Instead, we use the sample standard deviation. The formula is exactly same. Only in the denominator, instead of using the population standard deviation, we are going to use the sample standard deviation. In real life scenario, most of the time we do the student t-test only because we do not know the population standard deviation. Can you, let's say, you are conducting some kind of survey and the miles per gallon. Okay, you want to test whether the miles per gallon specified by the manufacturer is correct or not, but you suspect it cannot be the figure given by the manufacturer or the value given by the manufacturer. Let's say they say 25 miles per gallon. You want to test it, it cannot be 25 miles, it is less than. Okay, so in that case, to conduct the test, you do not know the, first of all, you do not know the population. You are simply hypothesizing based on the statement made by the manufacturer. He says 25 miles per hour. So you are saying that this is the population mean, but can you ask him what is the standard deviation? If you call Mahindra and Mahindra company and can you ask me, can you give me, so I could see that particular model of your car gives 25 miles per gallon, but what is the standard deviation? Will you give it? You will not give. In that case, obviously, right, you will have to conduct the t-test. You will not get the population standard deviation. Even if you ask them, they will ask you why the hell you are asking me population standard deviation, right? So you need to hypothesize whatever they say, and then what you're doing is you are calling your 10 or 15 friends, and then you're asking them, hey, how much miles per gallon it gives, and you are noting down all the from 15 friends, each of their mileages, and then take the mean and take the standard deviation. That is a sample standard deviation, sample mean. You have it, substitute the values and get the t-value. And in the case of t-test, right, it follows the t-distribution. The student test, it follows the t-distribution. It is similar to the normal distribution. In the case of z-test, it follows the normal distribution. So that's why look here, the z distribution is normal. We are assuming that the z-test assumes normal distribution, whereas t-test assumes t-distribution. It is the t-distribution also similar to the z-distribution, and except that it's spread out, okay, and wider in appearance and has a thicker tails. As the number of observation gets larger, the t-distribution becomes more and more like the shape of the normal distribution. If it is close to 30, smaller than 30, it will be this thing. So we know the central limit theorem. As per the central limit theorem, as the sample size is close to 30, it will become approximately normally distributed, right? So this is the t distribution. Next one is, what are the steps that are required to conduct the t-test? The only difference here is you need to find out the degrees of freedom. Sample size -1, that is what called as degrees of freedom. It is, otherwise it is same as your z-test only. Define the null and alternative hypothesis test. And this is a two-tail test. See, look here, in this case, as per the historical data, 6 years ago, indicated the average gross salary for a lead developer was 69,000. 6 years ago. This data is now outdated. Obviously, 6 years back, whatever the salary drawn by the lead developer was not same as the current lead developer salary, isn't it? Still, the EU and HR department, they want to test this figure against the current salary to see if the current salary is significantly different from the older ones. The number of samples taken are 12 and sample mean was 79,000 and standard. Sample standard deviation mean was given here. Only then you can do the, you should have sample. Only then you can do the t-test. But population mean was given here. Standard deviation is not there, population standard deviation. Hence, obviously, you need to do the t-test. Here, what you are doing is you are going to, define the null hypothesis like this. And it could be same. Okay, the 6 year back, whatever the salary drawn by lead developer was same as the current lead developer. So this is applicable. This is, basically this scenario is applicable for the recession time. I don't know how many of you are aware of this one. See, Obama, Obama, previous US president, when he took over the rule in USA, right? That time there was a lot of layoff. Okay, because most of the Americans, they lost their job. They were not able to repay the loan and all. That time, the US employees themselves, they came forward and they said, whatever salary you give, I'm okay to work because I have to pay my monthly bill. You know very well, in US, the employees' salary is very high, right? They charge hourly basis, $500, $600. That is also one of the reasons why they outsource it to other countries, the cheaper countries, right? If they outsource it to in India, so $30, $40 each cell per hour, you can do it, whereas they charge $200. They can hire, in India, the American company, they can hire 4 people. Instead of hiring one person there, they can hire, or whatever the money they give to one person, for that money, they can hire 4 people in India. So, but still Americans, right, they are okay to work for any salary. You just think that way, because of recession. So still HR wants to compare it. So this is the thing, and they want to compare. It could be less than the previous salary what they drawn, or it is greater than the previous salary. Okay. So you have the sample mean and hypothesized mean, sample standard deviation, all you get. So your t-value is 2.15. So your sample size is 12 and degrees of freedom, right? So 12 minus 1 is, what is 12? 12 is the sample size. N minus 1 is nothing but your degrees of freedom, 11. If the t-value is greater than 2.201, less than 2.201, so you need to, since it's a two-tail test, you need to find out the t values, right? So two critical value or something like that. You need to find the 2 critical value. Left side is minus 2.0, right side is 2.1. How did I get 2.201? You need to go and do a lookup in this table. T distribution table is pretty straightforward. So here, what is the degrees of freedom? What was the degrees of freedom? 11, right? Total samples is 12. 12 minus 1 was 11. So on the left side, you can see 11. Okay, and what is the alpha value? We have considered 0.05. So where it intersects these two values, 2.201. If it is a left tail test, minus 2.0. If it is a right tail test, 2.20. This is a critical value. And what is my t value? T is 2.15. Does 2.15 is greater than this value? No. Is that less than this value? No. Hence, it is not falling in the rejection region area. Hence, we fail to, and it is falling in the non-rejection region area. Hence, we conclude the current salary drawn by the lead developer and 6 years back, the salary drawn by the lead was more or less same because he failed to reject the null hypothesis. So far, so good. 6. Okay, so 1.5 hours I covered. And next we will take a look at two independent sample t-tests. This is also a pretty simple one. And everything is same. When it comes to t-test, remember that the sample size should be less than 30. And if you do not know population standard deviation, then you are supposed to conduct sample t-test, student t-test. Okay, and here now let us look at this one. So we need to compare the mean values of two normally distributed populations. So you have two populations. So let's say now I'm going to say male and female populations. Okay, the average amount spent by male is same as average amount spent by female. If somebody says, I want to test it out, no, the average amount spent by male is greater than female, right tail test or two tail test. If you want to conduct, we can do it. So we are interested in the difference between two independent groups. Okay, if the amount spent by the male and amount spent by the female, if you subtract these two values and if you get 0, then there is no significant difference. Okay. Okay, so what we are doing is obviously we cannot take the entire population data of both the male and female. Instead, we draw a sample from population 1, I call it sample A, and I draw a sample from population 2, I call it sample B. So to evaluate the mean difference between two populations, we sample from each population and compare the sample means on a given sample. And then what we do is, in this sample, what is the average amount spent by male? What is the average amount spent by female? We compare them and then we decide. Okay, so here in this case, the assumptions in the case of two independent sample t-test, two groups are supposed to be independent of one another. It should not be same. So one population was male and the other population is completely different, that was female. Okay, the dependent variable is normally distributed. What is the dependent variable? Amount spent. It is normally distributed. Okay, and the two groups. Now, if you ask this question, if the amount spent is not normally distributed, then you cannot conduct t-test. Okay, so it should be like this. The two groups have approximately equal variance on the dependent variable, and the violation of the assumption has been shown to be unimportant. See, the male and female, the amount spent, if you see the variance, right, it should be approximately equal, but it is not always possible. Hence, you can disregard this assumption. Okay, but it has to meet these two assumptions, fulfill these two assumptions. Okay, now let us work on this example so that you should be able to understand the two independent sample t-test. And look here, we have Walmart and Target customers. So let's say you are standing in front of Walmart, your staffs, and Target, also your employee staffs are standing there. And they are running a survey randomly with 85 customers. Here they are running a survey with 80 customers. And while talking to them, they note down each and every employee, each and every customer's average amount spent. So the Walmart customers, when we ran a survey with 85 customers randomly, we could understood the average spend by customer was $45 in here in Walmart, and similarly in Target $53. Now the standard deviation. So since we collected the sample of 85 customers of Walmart and 80 customers of Target, so we are able to find the standard deviation also. Now we need to find out, are there any difference between the amount spent by Walmart as well as the Target customers? So here you can define the null hypothesis like this, or slightly in a different way. S sub 0. So here we are assuming that both Walmart and Target customers average amount spent is, we don't see any difference. Right? There is no significant difference between the purchase amount or amount spent by Walmart and the mean purchase amount spent by Target. There is no significant difference. But in the alternative hypothesis, we are going to say, no, there is a difference between two. So next one is, this is the, we are going to list down all the things, okay? Because we have two samples. Two samples are independent. Walmart is different, Target is different. So Walmart related data is up to this one. And this is my Target data, okay? And this is my target. The second sample, first sample size is 85, second sample size is 80, and 45 is the X1 bar and X2 bar. This is Walmart average spend, Target average spend, standard deviation of Walmart. So, and here, if you want to, in this case, the degrees of freedom is slightly different. This total sample -1 is the degrees of freedom, that's what we discussed. But here we can find, we'll have to find out 2 degrees of freedom, and then we need to add them together. So what is the sample size here? 85 minus 1 degrees of freedom. In this case, the sample size is 80 minus 1. Add these two things, you get 163. This is your degrees of freedom. To infer about the average amount spent by Walmart and the average spent Target, the following is independence and assumption, normal. In this case, the purchase amount of customers is always independent of. See, it should be independent. Two groups are independent. That is what it says. Walmart is different from Target. Okay. Yes, we have sampled from two different retailers. Normality. Each group customers are greater than 40. So it can be said that the sampling distribution, the mean purchasing of each group approximately normal distribution. As per the central limit theorem, if the sample size is 40 or above, so it will become approximately normal. Yes, it meets these two assumptions. Then we are good to go with conducting the two independent sample t-test. Here, the step is different. Pooled to standard deviation purchase in Walmart and Target. Here, yes, pooled. You need to use this one. It's literally formula here. Yeah, that's all. Substitute the values, and you will get the yes pooled value as 20.056. And the next step is standard error of the difference the mean purchase on Walmart. And so you have a yes pooled and standard error pooled. For this formula, you need to use it. And after plugging in the value, you get the standard error pooled value you get, and standard pooled error you get, you have some value. And this is the formula. X2 minus X1 bar, 53 minus 55. This is Target average amount spent by the customer, average amount spent by Target customer, and divided by standard error pooled is 3.124, and X2 bar minus X1 bar, all these things put you get 2.56. So in this case, the p-value going to t-testing with degrees of freedom 163. Degrees of freedom is 163. In the table, you remember, in the left side, you will find 163, and the 0.05, you will find something, right? So you will get, in general, the p-value is 0.11376. Since the p-value is less than alpha, we are going to reject the null hypothesis, and we are going to say that there is a sufficient evidence to believe that the mean purchase of Walmart is not same. That is what we are going to conclude. See, if you have to do it manually, these many steps are there. And if you go and take up the interview with analytics company, they expect you to, use this formula on top. Okay. Otherwise, it is very simple. If you use a function, which is the built-in function, which is available as part of Python, right? Just one liner only. Just only one liner. Okay. And okay, next what we will do is we will continue the paired sample t-test. Probably I will take it up this one next weekend. Okay, we will finish the paired t-test also. Okay. So we discussed about two independent sample t-test because we have drawn these samples from two different populations. Now we will take a look at the dependent sample t-test. It is also called as paired sample t-test. So in this case, we are using a single sample. We are not using multiple sample here. Okay. So what is paired sample t-test? It's a strategy that is used to compare two population means in the case of two samples that are correlated. So it's basically the before after studies we do it. Okay. When the samples are the matched pairs or when it is a case control study, we sample from each population and compare the sampling. It's something like if you want to do some kind of before and after studies, in that kind of situation, you can use the dependent sample t-test. So this is the assumption is only the matched pairs can be used to perform the test. Okay, but in the previous case, the group should be independent, whereas here the group should be paired. Okay, and the normal distributions are assumed. So this is common for all type of test. Okay, and variance of two samples is equal. It is not always true. You can simply ignore. Cases must be independent of each other. Yes. Okay, now I'll ask you this question. Is there a significant difference in student score when taught through online and classroom training? So here you need to tell me what is the independent variable, what is the dependent variable? Which one depends on which one? The online or classroom training or the score? Does the student score depends on the online training or it depends on the classroom training? So the score is depending on dependent variable score, right? The score is depending on the mode of training. Hence, the dependent variable is score. Because this variable score depends on the type of mode. So what is an independent variable? Mode of training. Remember this, okay? So now you understood the difference between dependent variable and independent variable. Is there a significant people's pre-exercise weight and post-exercise weight? Now you tell me what is the dependent variable, what is the independent variable? Weight, you can say weight, right? So weight, and we can see pre-exercise. So what is the independent variable here? What is the dependent variable? Weight. Weight is the dependent variable, right? Continuous variable. And pre and post exercise are your independent variable. Because weight, your body weight can go high or less based on the exercise that you do. If you don't do any exercise, obviously your body you will become obese. And if you do exercise, so the weight is depending on your exercise. Your weight is driven by exercise. So part D test case study. Let's take a look at this one. Yeah. It's online training and offline training. Simply, I don't want to read the story and bore you. Okay. Basically, we want to check before and after training, what is the score of each employee. So this guy, each guy is before training their mark and after training. So let's say in your project, you're a project manager, you're managing 20 members team, and in your team, you could see that 10 employees, their performance is not up to the mark. And what you are doing is you are trying to train them the relevant skill set. After training, you want to check whether are there any improvement in the productivity or not. Got it? So that's all. That is what here the students, before training matched pair. Look here. Here we are conducting the matched pair t-test. Why? The same student before training, what is their mark, right? And then after training, what is their mark? Here the samples are depending on each other. This sample is depending on this sample, right? And here the cases are independent. Each person is different from. So this guy is before training, after training mark is not depending on other employees. Hence the cases are independent and it's a matched pair. So after giving the training, you are comparing this value with this value. You are matching this value with this one. That's why it's called the matched pair t-test. It's all formula, that's all. If you see so you have D bar. Look here on the right side. I mentioned the same thing. And the difference in score, 62 minus 50 is 12, and 40 minus 42 is minus 2. You are finding out the difference between post training and before training. You'll get somewhere. This is what called as a D, and you need to add all this value. You'll get 96 in total. The sum of D. Okay, if you add all this value, you will get the sum of D. That is what your numerator 96, and then the next one is the 12. What is the 12? The sample size, 12 employees. 2, 4, 6, 8, 10, 12 employees. The denominator to 18, you got it. So you got 8, sorry, you got, what is that here? You got 12. So D bar is 8. And then now you need to take the standard deviation. Standard deviation is not straightforward. You need to take square root of D squared divided by n minus 1 D squared divided by n into n minus 1. So here the D squared, if you square this one, 1122 divided by 11, sample size is 12 minus 1 is 11 minus. So here the overall thing, but you need to first square this value, 96 squared divided by 12 into 11. So if you standard deviation, you get this value. And end of the day, you need to plug in all these values. So what is the D bar? It's 8. Okay. And the denominator SD, we have 5.67 by square root of 12. The square root of n is the number of samples, 4.8. So T is 4.885. And if the degrees of freedom is 11 and alpha divided by 2, you are conducting 2 sample T test. And here what we are doing is 0.025. The critical values is 2.20. Since the T value is 4.8, it is more than the critical value. Hence, it is falling in the rejection region. We can reject the null hypothesis. Look here, the 4.885 is the T value. Since it is greater than the 2.20, that is the critical value, we are going to reject the null hypothesis. So even in the case of matched parity test also, we can use P value. But when you use any statistical software, it will give you the P value only. But along with that, you can find the critical value also. Okay. Hence, we are going to reject the null hypothesis, and we are going to say, we are going to conclude before and after training, there is a difference in the productivity. That is what we are going to conclude. To summarize, one sample test, it is measuring whether a sample value significant difference from a hypothesized value. That is what we are testing it out in one sample t test. An independent sample t test, comparing the means for 2 different groups. And paired summativity is used when each observation is one group is paired with a related other group. That is what we do it in these tests. Hope you understood all these 3 types of hypotheses. I'll give you some assignments. You can work on those assignments so that you should be able to understand all those things. Anyhow, will complete, in the interest of continuation, will complete the 2 types of error. The one is the type 1 error and the other one is type 2 error. What is type 1 error and type 2 error? So doctor falsely diagnosed a patient as having a disease, false positive. COVID is the classic example. Nowadays, everybody is aware of this term false positive and true positive. Actually, you know, a person is healthy, but my test shows, he is having this test, the COVID is positive. Let's say you are healthy, but the test says, the COVID test says you are positive. But actually you are healthy. That is false positive. Falsely, it gives positive. That is what called as type 1 error. And type 2 error, a jury finds an innocent defendant guilty. The rejected is 0. Defendant is innocent when they should not have. This is type 2 error. Okay, and this is one of the examples for the type 2 error. 1 second here. Just give me a second. I'm just getting 1 minute. Only 1 second. I just Okay. So type 1 error. So another example for the type 1 error. The jury finds an innocent defendant guilty. They rejected H0. Defendant is, when they should not have. Actually, he is an innocent, but because of my test value, let's say the t-test statistic value is less than the critical value, or p is less than alpha. Just because my p is less than alpha, I'm going to reject and say an innocent as a culprit, right? So this is also the another example of type error. The next one is type 2 error. The store manager finds an employee stealing, and here due to lack of evidence failed to reject H0. In this case, we are supposed to reject the null hypothesis, saying that employee is stealing. Let's say my null hypothesis is employee is stealing, but I fail to reject the null hypothesis because my field value is not less than alpha. Hence, I fail to reject the null hypothesis. Though I have seen an employee is stealing, due to lack of evidence, I fail to reject null hypothesis. This is type 2 error. So the type 1 error and type 2 error is very dangerous, okay, and very dangerous. Now we will take a look at when it is dangerous, when it is not so dangerous, and look at this example. So H sub 0, the person is good, whereas alternative hypothesis is bad customer. So here we say it is good, but null hypothesis true null hypothesis, right? This is alternative hypothesis. We say if it is good, sorry, here the bad and good. So reject the null hypothesis. Okay, actually a person is good, but we are rejecting the null hypothesis and we are going to say he is not a good guy. That is called your type 1 error, false positive. And the bad, this one, right? Actually, a person is bad. Okay, and we say it is okay. So okay, it is true positive. If you say someone bad, actually, if a person is bad, and if you conclude is bad, then it's a true positive. And good. So let's say a person is good, but as per your hypothesis testing, also it is good, right? Then it is okay. But whereas the person is actually good, but your test says is bad, right? Then that is called your false negative type 2 error. Okay, got it? Reject null. We claim something happened and it is true, and okay, better you can go by this one. Okay, so reject null. See, there are some situation you will have to reject it. There are some situation you have to accept it. Okay, so in the case of accepting certain thing, if you reject it, it is problem. That is what your false positive. There are situations you need to reject the null hypothesis, but if you fail to reject the null hypothesis, then you will end up with the false negative. Okay, so these are the two things that you need to remember it. The COVID is the classic example. Okay, false positive. Actually, okay, the another example is something like this. Okay, type 1 error and type 2 error. For example, let's take the same COVID thing. You are tested positive, but actually you are not having COVID. That is called your false positive. What is the false negative? The opposite. You are actually having a COVID, but your report says negative. It is called false negative. With this example, I hope you understood, right? It's very simple. If your report says positive and you are also sick, you are really having COVID and your report also positive, that's called too positive. But your report is positive, but you are healthy, that is called false positive. I just repeat the false negative. You are actually having fever, but your report says you don't have fever. It says false negative. You are negative, your report is negative, that is false. Actually, you are supposed to have positive. Okay, now you understood what is type 1 and type 2 error. Type 1 error is COVID, use a false positive, is nothing but type 1 error. And type 2 error is false negative. Actually, you have fever, but the report says negative. Got it? Any other questions? Any questions so far? Okay, since you don't have any questions, I'm going to wrap up the session. I'm going to upload this video, and the study material also you can find it in my website. I will also check it out. If it is not there, I will upload in the latest website, training. That's right, training info, right? Training in Chennai.info. I will upload it there, and watch my video. And what happened? The assignments. Please submit all the assignments, whatever I gave it to you before the upcoming Saturday. That is very much important. Okay. So, all right, guys, since you don't have any questions, I'm going to wrap up the session now. See you next weekend.